My name is Murali Emani. I'm from the Data Science group at ALCF. Today I'll be talking about how do we understand the deep learning workloads on running on different hardware. So in terms of how can we profile the application, what do we make of that sense of from the profile data, can we use that information back then where we can optimize my code better. So profiling is an approach that where we want to evaluate a program performance. So for example, if your program is composed of multiple steps, so we wanted to know like how much time does each of this function take in the application, and you can have more advanced level of profiling where we say like why is it taking so long. So basically this is a process where we want to identify what are the potential performance bottlenecks in terms of the compute resources, the memory, or in terms of the scaling bottlenecks. So there's a typical workflow for the optimization. So it follows that when you have an application, we want to profile the application, and from the profile you get some data that is generated. So you want to inspect and analyze the profile data, and we use it as a feedback to optimize the code, and we have to do this in terms of an iterative fashion where we try to get the desired performance. So in terms of a broad classification, so there could be multiple ways that the profilers work. So one is you can read the hardware counters. So hardware counters are those the counters that the numbers that you can read directly from the processors, and there are certain tools that you can actually read the raw values from. And you can also have some sort of sampling based where every couple of cycles you try to read the counters and get the snapshot of the values. And also in terms of the tracing, where based on each function call you can aggregate the collected profile information. So there are a plethora of tools that we can use for profiling. This could be for any general application. So in terms of both command line, and we have more interactive profilers which run on different types of hardware. We have something called as the perf tool, which runs on from the Linux kernel. We have the Intel Vtune, Open Speed Shop Tau, and for the GPUs, Nvidia GPUs, we have NVProf and Insight. So when you think in terms of profiling the deep neural net workloads, so we want to know that currently we are running these workloads on a wide variety of hardware. So we want to understand their performance and find ways to optimize them. But also we see that there's also increasing complexity in the models and the data. Now in terms when you're trying to implement a particular DNN, so there are multiple frameworks that we could use. So TensorFlow, PyTorch, MX, and for distributed we can use Horovod. So each of this particular framework will generate the appropriate functions or the kernels based on the hardware that we are running on. For example, if you're using these libraries like MKLDNN on the Intel machines, so you get corresponding kernels or functions for that, which is tuned for that system. Also, if you're running it on Nvidia GPU and you're using QDNN, so you try to get more optimized libraries, and those are those kernels which actually do the underlying computation for your model. So we want to understand if you're writing this code in a high level framework, how do we use those profilers which are focused from these say NVProf from Nvidia or Intel Vtune, and we get the data, can we use them back to tune my application? So there are a couple of challenges here. So one thing is profiling is a very time consuming process. There's a lot of overhead when we are trying to profile. For example, for a simple code that if you're using this NVProf on an Nvidia GPU, so the overhead could range anywhere from 3 times to 10 times the execution time. So that's a major challenge. So other challenge is that these tools generate a lot of data. So it's very hard to appreciate the data, and we want to understand which of the profile data would actually be useful for us. And as I said earlier, if you're trying to build more complex models in the workloads, so that actually further compounds the issue. So ideally we would want to have some sort of a strategy we want to use, and what kind of tools that we can use them to get the detailed insights from the profiling data. So I'll start with profiling the workloads on Nvidia GPUs. So the flow is that, so I'll try to give a high level picture of how can you use the NVProf to get the data and how can you analyze the data, followed by 1 or 2 examples. And if time permits, I also have some slides on profiling on the Intel using the Intel Vtune. So NVIDIA GPUs, the standard profiler is called as NVProf. So this can be invoked in a command line when you use NVProf in the command line, or you can also have it in a more interactive user interface using NVIDIA Visual Profiler. So there's a next gen profiler called as Nsight. So there's a Nsight Compute and Nsight Systems. So the Nsight has been released I think few years back, and the major reason was that they want to revamp the whole NVProf because this is it has a lot of overhead. But it relies on the same principles on what NVProf is currently implemented. So I'll go through some of the profiling strategies from NVProf. So when you use this bunch of commands, so you could use these options to list out what are your useful commands. So the goal here is that we want to capture something called as the metrics and events. So an event is a single countable activity that is read from a performance counter. So if you're trying to read some say memory related or the computed information, so each instance of that raw data is called as an event. And metric is something which is composed of a multiple events. So metric gives you a characteristic of an application, and that makes more sense to understand the application's execution. So generally we rely on metrics than events, and also in terms of the number of counters that are exposed to the application. So that depends on the kind of the GPU family. For example, on V100s, if you're using NVProf, so you can get at least 160 plus metrics. And if you're trying to have this on a multiple GPU, so the standard way is that the numbers are aggregated across all devices. So there are a bunch of ways that you can still fine tune what metrics we want on what devices we want to invoke on. So the typical workflow is you can have two ways. So one is if you're running in on a login node and a compute node. So what we do is we run the NVProf on the compute node. So basically this profiles my application, it collects the data, and it's dumped into a log file. And then from the login node you can use the visual profiler to load that profile data and do your analysis. Or the other way is that you can actually launch the NVP on compute node, but this is kind of a more heavy operation. So typically we follow the first step where we use NVProf, you collect the data on the compute nodes, and then we rely on the local nodes or on the login nodes to just understand the profile data. So it's typically you just set this the path variables, and then you're ready to launch the NVProf. So the multiple commands, I would like to highlight a few examples. So as I said earlier, so if your code has multiple functions, so in CUDA you're called as kernels. So if you're launching NVProf as is, so you get in the kernels in terms of the time each kernel takes. So you get a picture of what are the most heavy kernels, the hotspot kernels. So that gives you, and we will like what are the different functions or kernels in my code, and some ordering based on the timing. And the next step is, like, say if you want to get, so each kernel is composed of so basically each kernel is a computational part that is launched by multiple threads. So if you want to get more thread level information, the kernel characteristics, you could use print GPU traces for each of that kernel. So you get more kind of a trace information for each kernel. And say if you want to collect all kernels for all the metrics for all kernels, you can just pass the corresponding parameters. And the last two are where if you want to interactively invoke NVVP, the visual profiler, so you can just dump these metrics into a .nvprof file, and then you launch NVVP to upload the file and do the analysis. So as I said earlier, so the overhead is very large for NVProf. That could range from like 5 to 10 or 12x. So we want to minimize the overhead in terms of getting the data. So we use something called as a selective profiling. So basically we want to limit the scope of where we want to profile. Do we want to profile the whole code, or are there any selective regions of interest? So even NVProf has support for that, where you can pass the kernel name in the command line as an argument. So that will profile get the metrics only for that kernel. Say if I have 100 kernels in my code and there's just one kernel which is the most compute heavy, So I can just pass the kernel, only the single kernel name, and NVProf gives the metrics only for that kernel. So I'm significantly reducing the time. I'm not profiling the redundant kernels. Another step is, say, as I said, so they're almost like 150 or 170 metrics. So this other way that you can also pass which specific metrics that you want to collect in as one of those parameter. So a couple of ways that we can actually further fine tune is that if you want to profile only the heavy kernels, so the way of approach we use is we launch NVProf as is, so that gives you a timing analysis. So you know what are the most compute heavy kernels, and then you get those kernel names and you do this rerun this NVProf in the selective profiling mode. So in that way, so we are able to filter out the heavy kernels, and then we are profiling only for those kernels. Or the other way is, say, if I know what kind of kernels what kind of functions that I'm having based on the function name, I can pass that as a regular expression. For example, if my kernels so if I want to profile the kernels which are implementing the gem routines, so I can pass this regular expression in the kernel. So what this command does is it profiles only those kernels which are implementing the gem routines. So these are the multiple ways that we could use to significantly reduce the overhead when we are using NVProf. So if you are going a bit more detail at the hardware level, so this is a typical GPU memory hierarchy. So if you see that this is my kernel, that's my computational unit. So there's a different levels of hierarchy of the memory. So the first level you have this global texture local memories, and the next you have the L1 caches, then followed by the L2 caches. So this memory is something which is called as on-chip memory, and beyond that you actually have something called as off-chip memory. So that's where you have this device, this is called as the DRAM or the device memory. So if you're able to classify the memory access in terms of the on-chip memory versus off-chip memory, so this is one of the biggest potential bottleneck when we are running some codes on a GPU. If you want to analyze your code performance correspond to the memory behavior, and if you launch NVProf, so we could get, so this is just a subset of the metrics. So these are almost like 30 plus. So I'm highlighting a couple of them here. So these are the metrics that NVProf gives. But how do we understand which are important from this? So how do we make sense of that memory behavior from this data? So if you're trying to abstract out this information, we want to focus on only two of these memory axes. So if you see this, the arrows 1 and 2, so as I said, so these correspond to the access, so the reads and writes through the external memory. So that's you're getting the data from the device memory, and that involves a lot of overhead when we are trying to have this large amount of data transfers. That could be a bottleneck when you're measuring the performance. On the other hand, if you see the 15 and 16, so the kernel is associated with the loads and stores from the global memory. So global memory is the largest memory for the GPUs in capacity, and by default all the data is initialized in the global memory. So we are trying to focus on what parameters are most relevant if I want to characterize the memory behavior. So I can say these two metrics, the loads and store efficiency for the global memory, and the reads and writes from the DRAM. So you have combined metrics called as a DRAM utilization and global memory efficiency, which is able to capture these two metrics. So this example shows you like how can we get a high level overview of the memory behavior of application and to make a better sense of the large amount of profile data. So this table is giving a list of the most relevant or most important metrics that NVProf can give. So typically we are getting this 5 metrics out of 170 odd metrics. So these metrics are able to capture an application's performance based on, is it like a compute bound, it's a memory bound, or an IO bound. So for example, if you go with the first one, that's called as achieved occupancy. So if you see that, so this is something called as a warp. So warp is a bunch of threads which are running in parallel. So ideally we want all the threads to be active. So all threads have to be doing some computation. So the two extreme cases where there's very low work happening in the first case. In second case, like all threads are active and we were having a maximum utilization there. So the achieved occupancy metric reflects that how many warps are active and how many in a given cycle. So that gives a measure of are my GPU resources in terms of the compute resources, are they being used properly, and we want that to be like higher. So we want the threads to be doing some work. So I said there's the instructions and the load and stores count, which correspond to global memory, and the DRAM utilization will tell you in terms of what's the device memory transfers, that's referred to the peak, the throughput. So these metrics collectively give you a characterization of your application in terms of compute, memory, and I/O performance. So for example, we can have different possibilities. So say this graph is showing like the utilization in terms of compute and memory. So for example, if we observe these values are higher, so it means that both resources are highly utilized, which is a good thing. Or the other case where the compute is higher but memory is low, so we know that the kernel is kind of more compute bound. So there's minimal memory operations but a lot of compute related operations. So the other way is vice versa. And say if the values are both low, then there's something called as a latency bound. So we need to have a lot of overlap between the compute and the communication. So this is not that a good scenario. So if you're using the NVVP, the visual profiler, so once you launch the user interface, so you can actually select if you want to profile individual kernel. So these are the list of kernels. So it's one sample example. So you can pick what kernel that you want, and you perform a detailed kernel analysis. So for example, this graph is telling you for that kernel what's the compute and the memory utilization. We see that there's a lot of memory related operations. So we know that that particular function or kernel is kind of bound by the memory, and also in terms of memory it's bound by the L2 cache. So this is able to tell you that we should be able to optimize the code which is bounded by the memory operations. So some of the tips are we want to start with NVProf first, and we want to profile and go a finer level of analysis only when the kernel takes a significant amount of time. And also it depends on the hardware that we are using and what's the maximum achievable performance. And as I said earlier, this is kind of an iterative workflow where you want to profile your code, get the profile, observe the data, and then can you make some changes which can lead to improvement in the performance. So for example, if this is a simple CNN code, this is with, on a KRS with TF TensorFlow background. So if you want to run this code and profile, so what we could do at a high level is that we want to import a profiler, a selective thing called as Numba. Numba is a JIT compiled Python. So when we import that, so we could actually, so model.fit is where the model training is actually occurring. So we want to limit the scope of my profiling here. So I say this CUDA profile start and the CUDA profile stop. So I am able to pass these parameters from my high level code, and when I run NVProf, so my NVProf is collecting the profile information. So the TensorFlow GPU will generate the underlying corresponding CUDA kernels, and when those CUDA kernels are executed, so my NVProf is collecting those metrics. So the first strategy that I said that we do that we generate the NVProf, we filter out what are the heavy kernels. So we plot these kernels along with those 5 metrics. So this is a plot which shows the DRAM utilization normalized from 0 to 10, and the kernels are on the y-axis. So how many kernels you want to pick is depending on your specific application. So here the cutoff was, so I have filtered out the kernels based on the percentage of execution time which are more than 5%. So you can actually have a threshold where you want to have a cutoff, like I want to profile only the kernels which take like 50 or 60% more. So this will tell you like my kernels are on the y-axis and what's the DRAM utilization. So as I said earlier, so DRAM utilization is where how much data reads and writes I'm doing from the external memory, and ideally we want that to be a lower number because the data transfers could incur a lot of overhead. And similarly the same plot with the IPCs, and this is the achieved occupancy, and this is the global memory efficiency. So as I said, so it depends on what metric that I am considering. Is it the IPCs, the memory efficiency, or the DRAM utilization? And these are my kernels. So once I do a selective profiling, I am profiling a particular section of my code. I am able to generate these plots. So I am finding out which kernels are heavy and what are the characteristics of each of that kernel. So then I can get a more detailed understanding of these are my kernels which are compute bound, these are memory bound. So the other question is how can I use this information in the workflow? So I have to use this information somehow and go back and tune my application. So it's a very hard problem. So you could do some high level changes at the Python code where I'm trying to change some of those parameters in my architecture, or can I change some of the CUDA kernels? That's kind of hard. So we'll see that say if I'm able to change this the number of the batches. So I'm trying this information and I'm varying my batch size. So I'm rerunning the same workflow with varying batch sizes. So I can see that some of the kernels are actually showing a different performance. For example, if we have this the SGM routine, so you see that with the batch size varying, the IPCs are also varying. So similarly, some of the kernels actually demonstrate a significant change when you're changing the model parameters. But for example, here, if you're using the SGM 64x64, it's kind of not much affected with the batch. It's almost the same value. So what we want to do is we want to get these measures of the graphs from the metrics. We want to use that information somehow, change those parameters, rerun, and we want to measure, see, if I want to optimize, say, minimizing the DRAM utilization, by changing the batch size, I have to see a reduction in the DRAM utilization. So that means my model is doing good in terms of utilizing the DRAM. So that's why we want to have this loop of the iterative profiling. And similarly with occupancies and the memory efficiencies. This is kind of a very generic and very high level overview of characterization. So it depends on what framework we are using, what is the model that you are profiling, and what kind of GPU, what kernels that you want to do. So it needs a lot of involvement in trying to understanding the code much better. And this is you observe the performance, you tweak your code back, change the parameters, you measure the performance, and that's how you come to a stage where you say, okay, my model is able to make the best use of the underlying resources. As another example, say this is an LSTM. So taken from this slides from Nvidia. So this is a bunch of recurrent layers where you have these cells, each of these cells, and each of this LSTM cell is actually doing some matrix multiplication, and it's taking the parameters I and the other parameters, it's computing the memory, it's computing the operations there. And say if you want to profile this LSTM with this parameter, so this is my mini batch size, my hidden layer size. So if you run this nvprof as is, so I said, so the top chunk tells you what are the different kernels, CUDA kernels, and what is the percentage of time. So here we see that almost 93% of the time is spent on this SGM routine. So we know that's the most the compute heavy kernel. And APIs are something which are relevant to CUDA, so you can ignore them. So we are focusing on the kernels which are run on the GPU. Now the other thing is, say if you are having large amount of data, as I said, so we want to understand how can we optimize this much better. So in terms of the data transfer, so we want to minimize the data transfer overhead. So one of the optimization that we could do is, say if you are doing this, say A1 to A4, you are doing this matrix multiplications. So can we combine those the arrays A and correspondingly they multiply with H? So that is going to result in, we are trying to reorganize the code where we are trying to combine small data transfers, a chunk of small data transfers, and we want to minimize that to a few large data transfers. So that's one of the optimization way that we could actually use. So this optimization you could do at the CUDA and the algorithmic level or the CUDA level. So in terms of tweaking this at the Python code, so this is similar to like how do you change those batch sizes. So when you do this optimization, so the first thing, so this is the time which is taken. So there are 8 calls to that particular kernel. So the average time is like 72 microseconds. So when we are able to club those data and implement optimization, so we are able to minimize the number of calls here, and that's also dropping down this execution time. So with this simple optimization, we are able to gain at least 2.5 to 2.8 times the performance gain, and the code is able to execute much faster. So as I said, so these 2 examples will tell you, say from the NVProf, how can we use that information. So you can change those model parameters, or can you change the algorithm itself, and how can you see that by changing those parameters you are able to get a better performance. Okay, so I'll also continue. So this is a strategy which we use for on Nvidia GPUs using NVProf. So the similar strategy we want to use when we're running these codes on the CPU, and we want to profile using Vtunes. So Vtune is also is a profiler where we want to analyze what are the heavy functions or heavy kernels, and how much time is spent on these kernels, and in terms of concurrency, multi-threading. So it gives a coherent picture of the underlying implementation. So Vtune has something called as analysis groups. So there are multiple analysis groups that we could use, and I'm listing few of them here. So one is called as the hotspots. So hotspots is where this group will tell you what are the most compute heavy functions in your code. And the other, so there's something called advanced hotspots, which is most widely used, but in the latest versions this is kind of deprecated and this is integrated into hotspots. And the other group is something called as the memory consumption. We want to understand like how much memory is consumed by the code. And the other group is called as the microarchitectural exploration. This gives a more finer level of information from the hardware characteristics, also trying to understand in terms of the memory access patterns and the bandwidth related information. Okay, let's get this. So one of the high level thing is similar to NVProf is something called as APS, the application performance snapshot. So all it needs is once you have this installed with the license, so you can just set the variables, and launching with APS will actually tell you a high level overall picture of your code. For example, how much time your code is taking, what are the number of cycles per instruction, and what's the utilization of the CPU. So anything to do with this, the red marks, so that tells you that that's not good metric. So this way that you can actually tune that metric. So APS gives you a high level snapshot. This gives you, like, if you want to run, this is similar to the NVProf, where NVProf gives you, these are the high level kernels, they take this amount of time, and APS gives you a similar related information. Okay. And the other thing is called as the hotspots. So when you use this in the command line, so you use this parameter using an op called as collect. So that's the action that you take. So you're collecting the hotspots, and you can actually dump that into an output file. There's something called as a finalization mode, where you're trying to aggregate all of the data. So other strategy here is that we run this Vtune on the compute nodes without finalization, because we want to do the finalization on the login nodes. So we don't want to spend more time in the compute nodes aggregating all those individual chunks of data. So we pass that as the finalization mode as none, where we are trying to just profile the data and get the information. But from our experience, it's kind of scalability is an issue where we want to scale this to a large number of nodes. Hotspots is something which actually doesn't perform well in that scenario. And the other knob that we could use with hotspots is something called as the sampling mode. So you could use a software mode or a hardware mode. So software mode is the default sampling mode, where if you're having this code, you're trying to profile all of the functions in your code along with what are the internal Python and the runtimes and the Intel runtimes. So if you're using the Vtune as is, so you're actually using the software sampling mode. And as I said earlier, so advanced hotspots is kind of integrated into the hotspots, where you have to pass the sampling mode as hardware. So this will actually profile all processes. So this is kind of a more detailed and high level profile information. So you get lots of data from that. So hotspots is something advanced hotspots where it also keep tracks of the call stacks, the context switches, cycle per instructions for all of them. It relies on the kernel driver, the Vtune amplifier kernel driver. So in trying to optimize it, if you want to minimize the time spent to profile the data, you could actually use that at a lower frequency sampling. So advanced hotspots has, if you're using the sampling mode as hardware, so by default you are telling the kernel that you want to sample at lower frequency. So you're trying to minimize the overhead in profiling. So as I said, so once you do this finalization mode as none and you run this profiling script, so you have all this the raw data, and in the login node what you could do is you could use the finalize step where you collect all those collected profile information, and you could ready to use the profile information now. So similar to NVProf, so you could also use this in two ways. So you could use the command line, get the metrics, get the information, or you could use an interactive profiling where you want to use a user interface. So if you want to use the user interface, you can launch using this command. And so this graph is, so this is a user interface snapshot. So this tells you a bunch of metrics. So what are the different kernels, what are the different compute times, and all those corresponding metrics for each of the kernel. And this plot below shows what are the threading level operations. So if you have launching using multiple threads, so how are the threads executing in terms of the timeline. There are like pros and cons for this. So you can actually visualize all the functions from your code, but it's hard to trace back to your source code, like which line of my code is actually causing this bottleneck. So that's kind of hard to trace back. And the other analysis group is called as the microarchitectural exploration. So this is telling you, so these are my functions here, and in terms of the metrics are related to the memory bound. So is it like L1, L2, L3, or the DRAM bound, and it gives the numbers for that. And this pictorial representation will tell you if my instructions are doing the computation, or do they spend a lot of time in waiting for the memory. So anything to do with red is flagged. So it's not a good case. So there's a lot of ways that you can actually that's a potential scope for improvement over there. So this picture will tell you if you're launching in using this memory mode, if my code has different kernels, and by picking each of these kernels, you're able to see is that bounded by the memory or the external DRAM memory. This is something similar to the DRAM utilization metrics we have seen at NVProf. So you're trying to characterize the kernels and the application in terms of the global memory and the external DRAM memory. So the same thing, you can use the microarchitectural exploration by passing this as a parameter, and there are multiple knobs that you could use. So one is if you want to collect on the memory bandwidth here, or if you want to focus on the DRAM bandwidth, so you could actually choose that. So you could use multiple knobs when you're launching this microarchitectural exploration group, and you get corresponding profiling data for that group. And I said, so the tuning is depending on what architecture that we are running on and what model that we are using. So there are multiple recommended strategies or guidelines that we could refer to when we are trying to use Vtune for understanding this profile data. And also in terms of the memory access, so this is an example which tells you, so these are my different functions which are having this metrics like the time, the memory bound, the load stores. So you're trying to measure what's the bandwidth information for each of those functions. So I'm taking the same code. So right now I'm running this on using the Vtune. So I'll present if you're trying to get that raw data and if you want to filter out those metrics and get some information. So the y-axis is showing what are the heavy kernels. You could also use MKL, DNN, verbose mode that will actually sort out the information based on which kernels are taking a lot of time. So if you see that there's a convolution, the backward which is working on the weights, so that's actually taking a larger chunk of time, followed by the data. So these are the most heavy operations in my code. And if I want to get those metrics for these kernels, so this is a simple example, not the exhaustive metrics, similar to what you've seen at NVProf. So this is the first plot will tell you what are the L1 cache misses. So the cache misses occurs when your memory does not fit and your data is not in the memory, so you have to read the data from your external memory. So if you see that the convolution backward with the weights, so that's actually reported a larger value for that. So it means that it's bound by reading the data from the memory. Though it's a convolution operation, it actually does a lot of computation because of the increased number of weights, so it also has to do lots of reads and writes. And similarly, in terms of what are the stalls, like is your application bound by these memory stalls, or is it waiting for something for any further instructions? So there's a couple of metrics that we could use to analyze how each of my heavy kernels are reporting these particular metric numbers. So these plots will show you a brief characterization of my the hardware level implementation of my kernels, and are they bound by the compute memory or IO parameters. So some of the things we could analyze that, like convolution layers is more of compute bound, so it's bound by the computing resources, and dense layers is kind of more sensitive to communication, and that's the bandwidth information. So this is one use case where even after having this custom installation of TensorFlow, there's a lot of room for improvement. So when this was profiled with Vtune and we sorted out based on the heavy operations, so FFT was the most heavy operation, and this was not it's kind of not the optimal implementation. So we actually replaced that with the NumPy, and we are able to get a better performance. So using this Vtune, we are able to get the profile data. You know which kernel or which section of your code is actually taking a lot of time. Then you could focus your efforts on trying to optimize that particular kernel. So in what ways can we use this information back and tweak our code at a higher level? For example, if you're using this TensorFlow, you could change some of the parameters like the intra-op parallel threads and intra-op parallel threads. So if you see this plot here, so we see that there's a significant difference of the throughput when you're trying to measure the performance. This is on the KNL nodes. So when we are trying to change the inter threads and the intra-parallel threads, so based on the metrics, we could actually go back to our code and see, okay, this is my application. What parameters could I change? So you could change the batches, the batch size. That's the most obvious thing. And the other thing is, so if you want to change the batch size, so that will also have a direct impact on the memory aspect, but also we have to make sure that we are not compromising more on the accuracy. So it's kind of a trade-off. So we want to figure that out. Like by changing those high-level parameters, we are able to get a better performance in terms of the observed metrics by not compromising on the accuracy. So a bunch of, as I said, bunch of resources where you can actually read like how can you tune your applications further. The recommended strategies, recommended ways to do that, and as I said, so it depends on, there's no straightforward solution, so it depends on your model, it depends on your framework, it depends on your underlying hardware. So it's kind of a more, needs more fine level of understanding. And it's a couple of commands, useful commands we could use to get what kind of information that we want, like say the hotspots, microarchitectural exploration, the memory consumption, or if you want to change the sampling interval to reduce the overhead. And say there's something called a summary mode, so you collect all these hardware events, you want to get only a summary of all those cluttered metrics instead of individual numbers. And there are multiple ways. You could also set this MK, if you're using MKLDN, and you could set this verbose mode, so that will give you more information which you could use to further profile and optimize your code. And yep, so there's a lot of active projects going on, a lot of good work. I said because this is kind of a very hard problem to do, because I said in the iterative workflow cycle, so you have your code, you have a lot of tools available, you are profiling the data, but how do you use that data? So that's the biggest question. So there's a lot of projects, lot of development of tools that's happening where we can use that profiling data. Can we build some models that could automatically tell you, hey, we have observed this profile data from your code, this is the hardware, can we get some feedback to my application that I could use it to further tweak my code? So it's not that we want to rely on an expert to sit down, understand the Vtune logs or the NVProf logs, understand the data and then try to tweak the code. So can we do some sort of a performance modeling and try to get more automated way of understanding your characteristics of the code and then trying to optimize the code further?